So electron configurations can be a challenging subject. If you're finding that you're struggling with this, that's okay. Take your time, schedule an appointment with me if you need to, and we can work through it and you'll get there. So the first rule we need to look at when we look at electron configuration is the Aufbau principle. This is a rule that states that electrons occupy the lowest energy orbital available. And so that looks something like this. Here's a model that demonstrates where the electrons can go. And so if you look at this, you can see that 1s is the lowest level available, then 2s, then 2p, then 3s, then 3p. But when it comes to 4s and 3d, you can actually see that the 3d is at a higher level, or higher, the orbital is at a higher level than the 4s. So before going to the 3d, electrons will go to the 4s, then the 3d, then the 4p, then they will go to the 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, and 7p. So here's our second rule when writing electron configurations. It's called the Pauli exclusion principle. And it states that only 2 electrons can fit in an orbital, and that each electron has opposite spin. The third rule is Hund's rule. So Hund's rule states that every orbital in a sublevel must have 1 electron before any of the orbitals will get a second electron. So let's look at an example or a model to show us how these rules work. So I'm going to drag these electrons here into the orbitals. And so we can drag one to our 1s. And remember that each orbital can hold 2 electrons. We can drag a second one down there. We can have 2 electrons in that orbital, and now it's full. We can do the same thing for the 2s. We can fill it up with 1 and 2 electrons. And now it is full. Now we can start to put the electrons in the 2p level. And according to the rules, we have to put 1 electron in each before we start to double up. So this might be like sitting on the bus. If there are enough seats available, you would each take your own seat before you would start to double up. But once all of the seats are full, then you're forced to double up with someone else. And so you fill up the orbitals one at a time. So that's how electron configuration works, and how you'll see that the electrons fill up the orbitals. So we continue to 3s, 3p, and so on. I'm going to walk through an example of showing how an electron configuration would be written. So first off, the first thing you put is a number that represents the energy level. Second, you write a letter which represents the orbital or the sublevel. Finally, you write a number as superscript. Note that it's written above, and that represents the number of electrons that are in the previous sublevel. Then, if you have more electrons, you continue to write the next energy level, the next sublevel within that energy level, and the number of electrons that are in that sublevel. So also I would like you to notice this outermost energy level, sublevel, and the number of electrons in the sublevel. The last one doesn't have to have a full sublevel. You may have a partially filled sublevel. Everything prior to that has to be completely full. So this has to be a 2 because that is the maximum number of electrons that goes in the S. So you've seen this before, and we've used it to know where the electrons are going to go next. We've got our 1s here, I've written in a 2 to model that that is the maximum number of electrons that can go there. And so I've written that in for all the s's, I put 2's. For all the p's, I put 6. For all of the d's, we put 10. And for all of the f's, we put 14. And so that is the maximum amount you can put in each. If you add all of these up, you get 118 electrons. So here are some examples of electron configurations that have been written out. We've got hydrogen with 1 electron. So we write in that it's the first energy level, S is the sublevel, and there's 1 electron. Helium has 2 electrons, so we write in 1 is the energy level, S is the sublevel, and we put 2 electrons in there. Now that sublevel is full, so we move on to lithium with 3 electrons. We write in a 1, an S, a 2, it's full, so we go to the second energy level. We go to the S orbital, and we put 1 electron in there for 3. Beryllium, 1s2, 2s2, for a total of 4 electrons. And boron, we do 1s2, 2s2, 2p1, for a total of 5 electrons. The pattern continues with carbon being 1s2, 2s2, 2p2, nitrogen, 1s2, 2s2, 2p3, and so on. And so feel free to pause the video and look through these if you need any examples to look at. And hopefully that's helpful as you're learning about how to write electron configurations. I've got the first 25 here. Again, thing to remember is that the only thing that's going to be changing is your outermost level, and that's the only one that's allowed to have an incomplete or unfilled shell. So here we're going to start talking about abbreviated electron configurations. And you can notice I've highlighted this section over here of the periodic table. So with helium, the first energy level fills up when the s orbital fills up and it's full. The rest of these are highlighted because they occur when their p orbitals are full. So with abbreviated configurations, we're going to be using them as a way of writing out the electron configurations. So here's some examples of abbreviated configurations. So the electron configuration for helium is 1s2. The electron configuration for carbon is 1s2, 2s2, 2p2. And so if you look at it, this 1s2 part is the same as what's read here on carbons. So that can be replaced by taking brackets, writing in the symbol for helium, and then writing the rest of carbon's electron configuration. The same thing here. So neon's electron configuration is 1s2, 2s2, 2p6, which matches this red part of chlorine's electron configuration. And so you can replace that with brackets and neon symbol, and then the rest of chlorine's electron configuration. Same here with potassium. We can use argon's electron configuration and use that in place of this portion of potassium's electron configuration. Put it in brackets, argon symbol, close bracket, and 4s1, and that is potassium's abbreviated electron configuration. And this is our last example, so we're using argon again with titanium. Argon's electron configuration represents the first part, and then you put that in brackets, and then you have 4s2 and 3d2, and that is titanium's abbreviated electron configuration.